In this particular lecture, I want to dive into showing off how reinforcement learning is actually training a model on a discrete environment space. A lot of people have conceptions when it comes to reinforcement learning that it's video game driven, etc., because that's a lot of what we utilize for these models, right? For training them is kind of like video game type of environments. But that's just because video game type of environments serve as a good box for these models. And that's exactly what it is, right? We're creating a box of a discrete environment. And creating discrete environments is what we do as people all of the time, right? Creating boundaries, borders, countries, continents, etc. These are discrete boundaries and discrete environments. And then what we're doing with reinforcement learning is we're doing this same thing, but within mathematical spaces as opposed to physical spaces. And mathematical spaces follow a lot of the same rules as physical spaces. The laws of physics, for example, entropy, thermodynamics, etc., exist within these mathematical spaces as well. And that's an important concept to draw upon because a lot of how we train the models within these spaces relies on these physics concepts. But breaking this down and kind of visualizing this, what does this mean, right? And so, again, I can create and uh, visualize any sort of environment that I would like, right? And so let's create an example here. And this is evolution.py. And this is one of a cool one of my favorite ones here. I'll let this go and then we'll look at the code here on the side like this. Oh, there we go. Bring that out there. So, and then so what we're looking at here, and this is to me visualizes this concept very well, right? Because this is an environment of one-celled organisms. Each little circle is a one-celled organism, and then they're just going about their environment. Each one has a fitness score. And they go and interact with each one of the different agents. The little green in here is food they're picking up off of and then going through, right? And it's very simple. And that's the environment. And then their environment here is a literal box, and we have literal agents that are represented as literal dots that are going through and moving throughout the environment. And then I just define that via this code, right? And then so I have, I'm defining the simulation, I'm defining exactly what the box looks like, and then everything that goes within the box, right? Here's all of the math within the box, here's your environment, and then we're literally returning the environment, right? That's what the return is here's your box. And then we want that back, and then when we create our box, we need to put agents in the box. So these little dots, here's how the dots work, right? And then so here's what their process is, and they have a mutation process, and they have DNA, etc. Right? And then so they go through, and then they have again their fitness score, and they can reproduce and create offspring, and then that's what they're doing, right? They're going through and they're feeding and eating, and then creating offspring. And then their offspring has mutated fitness scores, and then that's kind of randomized, but then also based off of like the survival of the fittest, right? So we have natural selection going on within this environment. And then we create our full simulation. And then when we do this, it ends up being a grid, right? So we have grid size, population size, DNA length, and mutation rate. So we're defining an environment, we're defining agents, and we're defining variables within the environment. And that's very simplistic overall as to what we're doing, right? The environment, the variables, and the agent within the environment. And then so within reinforcement learning overall, no matter what the concept is, no matter what the environment is, that's exactly what we're doing. And this environment can be lots of different things, right? So it doesn't have to be that literal environment that we're just looking at there. We can take it a step further and go kind of more conceptual with it, right? Let me find a good conceptual example here that would be best to show you on, I think this one, Object Simulator. Let me try this one. Awesome. And then so what this one is measuring very specifically, we want to take a look at this graph. Look at the graph here on the right. The graph on the right is always going to go down over time, right? There's going to be deviations within the short term, which is cool and is expected, right? But what we're measuring within this is we're measuring a decrease of entropy and then an increase of clustering. So essentially, we're measuring the physics within the environment. And knowing the laws of physics, I can tell you that within this environment, that this graph on this right is always going to go down 100% of the time. It's going to decrease over time, right? That's just what it will do. And then I can also tell you that these agents on the right, these little dots on the right, they're going to become closer and closer together to one another as time goes on, and that's what's being represented there on the right-hand side and what we're visualizing and seeing within this, right? And that's just kind of how this does. And then so this is, again, the environment. And then so it's very straightforward in this instance, again, that the environment is a box. And then when we're looking at like Atari games, we can take that a step further, right? Like the screen, the whole entire screen that's going on within that is the box. But then this box concept is to me is important, right? Because everything that's happening, like literally what we're doing is we're just putting, again, we need an environment, so we need the box, and then we need to define what goes on within the box, and then we need to put agents in the box, and then that's it, like the rules of the box and the agents in the box. And then so to me, this is kind of like a magic box, right? Like this box can be anything. In the previous example that we were looking at, the box was agents that are evolving. And this example is just little dots that are clustering. And then in this, so we've looked at like 2 examples of dots so far, right? But it doesn't have to be dots. It can be very far away from dots. Let's say, for example, I want to do, like, for example, like a more real world, I want to have it make an API call. I want to have our agents go out, and then in this instance, they're going to collect cat facts, and they're going to collect them from an API source. And then they just did that, right? So cat facts is saved to this text file that they just created. And then let's go ahead and take a look at the text file that they just created. Here we go. This one is the most recent one. And then cat facts. Cats can get tapeworms from eating mice, which is unfortunate. If your cat catches a mouse, it's best to take the prize away from it. Your cat recognizes your voice, but just acts too cool to care, probably because they are. And 3, in tigers and tabbies, the middle of the tongue is covered in backward pointing spines used for breaking off and gripping meat. Kind of crazy cat facts there, but there they are. And then so in this instance, we created an environment, but an API call in this instance, right? And then we had our agents go out. And that's what I want to very specifically mention and think of and get you to understand these concepts is, yes, an API call. I can literally make my environment an API call. I can literally make my environment an Excel spreadsheet. I can literally make my environment a PDF document. I can make it multiple Excel spreadsheets, multiple PDF documents. It could be multiple programs working together. The environment could consist of 2 programs with an API call in the middle. And then all of these things are defined out, right? And then just illustrating this for you and taking that deeper, right? It doesn't have to be what you would normally think of as an environment. Let's take another example here where I can look at like board.py, which is kind of the same thing, right? But we're invoking an LM model at this point. So I can invoke multiple agents within this and multiple frameworks. So whatever my environment is, I'm just defining multiple variables within the environment, right? And I'm just literally taking code, whatever it is. In this instance, I have several of these built out, right? I can show you Atari games, etc. But all the concept that I'm trying to illustrate within this is that all of this is environments. And then so how does this work mathematically? Kind of giving you that framework and understanding overall. These work mathematically via a concept called Gaussian probability, which is the same type of concept that's necessary for backpropagation, right? And then so you have different probability mechanisms, and then different ways that the computer can model probability. And then so in this instance, we're just creating a Gaussian space and defining that within and utilizing Gaussian probability and Gaussian distribution. It's also noted that within this, a lot of these files that I have built out also utilize Monte Carlo algorithms and Monte Carlo probability. But the Monte Carlo probability is, I utilize it for simulations within the environment, right? So the environment itself, the construction, the box is always going to be Gaussian probability. The box itself will always be constructed out of Gaussian probability. But if I want to simulate actions within the box, simulate the variables interacting with the agents within the box, then that's Monte Carlo probability. I'm running simulations, and that's what Monte Carlo is, right? Monte Carlo probability is simulation based, and it's running simulations off of these actions. So I can define the box, define the terms of the box, and then run simulations off of the box. And then the majorly fascinating thing about this, what is kind of trippy about this is that I don't need to know all of the variables within the box, right? If I can define enough of the variables that exist within this box, then I can figure out every other variable from there. So if I have an optimization problem, if I don't know what the best route is, what my best optimization time is, what my best way to service my customers are, but if I know a lot of other variables, I can plug in all of those other variables. I just plug those in, and then it spits out and computes based off of that the answer and the real answer, right? And then so I start off in a lot of instances with fake data. Like I'm initializing the weights based off of concepts. I'm just making up the concept. Here's a definition of this concept. Here you go and run with it. And then for whatever reason in these environments, given enough time and enough probability, the model's able to figure it out and spit out a real actual answer. So to me, these kind of work out like magic boxes, right? Magic probability boxes. That's exactly what we're dealing with. And the magic probability box can be anything. It can be any business-related process or any process in general. But so generalizing it to business-related processes is that next level, right? Your business can become like a video game, literally processing and inputting the variables and the agents of your business within that. And it becomes like a second entity and a second simulation of your business overall. And that's kind of where I'll end this, right? Is that this is the philosophical bridge from getting to and from reinforcement learning as like Atari and video games to this concept of utilizing reinforcement learning specifically for businesses. See you in the next lecture. Thank you very much.